All right, so for this next one, we want to go ahead and rank the torques produced by these four different forces from greatest to least. So the thing I noticed right off the bat is A has the biggest radius. It also has the biggest amount of force. And to top it all off, the angle for torque A, or for force A, would be 90 degrees. So that has to be the greatest amount of torque. Okay. Again, the whole time I'm going to be thinking about this equation here: torque equals RF sine theta. The next one, okay, I look here at smaller forces. I see C here is a big radius, but the angle between the force and that radius is actually going to be 0. So the torque produced by force C is actually equal to 0. So that's actually going to be the smallest one. So I'm going to move on in and look at the difference between B and D. Same force, same radius. The key difference, though, is that angle. B is perpendicular, whereas D is not going to be perpendicular. So we're not going to get as much force with D. Remember that 90 produces, or as much torque, I should say. Remember that 90 produces the greatest amount of torque. So A is going to be greater than the torque produced by B, which is going to be greater than the torque produced by D, which is going to be greater than the torque produced by C. For the next question, will the object accelerate clockwise or counterclockwise? I'm going to go ahead and think about the directions for each. So A is going to cause counterclockwise rotation. B is going to cause counterclockwise rotation as well. C doesn't do anything, and D is also going to cause clockwise rotation. So we have A and B, our two biggest torques, and we know actually that B by itself is bigger than D. So with the addition of A, this is going to rotate counterclockwise. All right, so for this one, we want to rank how difficult it would be to cause each of these objects to accelerate angularly. So really what we're thinking about is moment of inertia. All right, and with that, we know that I is equal to mr squared. So the things we're really thinking about is the amount of mass that we have and how far that mass is from our pivot point. So starting with the least, okay, we see here that if we have a 2m mass directly in the center, all right, although that's a decent amount of mass, it's right on the pivot. So our R value here would be 0. So that actually is going to be the lowest moment of inertia. The moment of inertia of object A is going to be less than, and we look now at the remaining objects. So B has a big mass and it's on the outside, so that one's not going to be the next smallest. So we're going to look between C and D, both of which have a mass of m, but C has a mass closer to the pivot. And then it's going to be D, which has a mass further away, but that is going to be less than B, because even though the masses are at the same location, B is 2m versus that single m. For this problem, we have a situation where there's masses attached with strings to various wheels that are accelerating the wheel. At point A is the instant after the system is being released. B, it's falling. C is when the box first hits the ground. And then D, we see that the string releases here. And so the first thing we want to do is we want to rank the tangential accelerations of a point on the edge of the wheel at each point in time. And so for that, we're going to be thinking about the fact that the tangential acceleration of the wheel is going to be equal to r times the angular acceleration. Since we're always going to have the same radius, really what's going to be key is this angular acceleration piece. Whenever the angular acceleration is high, our tangential acceleration is going to be high. And so really, A and B, in both cases, we're going to have a force of tension here from the box pulling on the wheel, okay, creating a torque. So we're going to have a angular acceleration at those points. However, once the box hits the ground and after the string releases, we no longer have that pulling force, okay? And so that means we no longer have an angular acceleration, and therefore we no longer have a tangential. So for our ranking here, C and D are obviously going to be the smallest, and they're equal to each other because we have 0 angular acceleration, therefore 0 tangential, and they're less than A and B, which are equal to each other because there we have a tangential acceleration, but it's the same torque, same moment of inertia, so same tangential acceleration. The other thing we're asked to do is draw the velocity versus time graph, the angular velocity versus time graph for this situation. So I'm just going to label these points A, B, C, and D. And what we're going to have is we're going to be speeding up from A through C, and then we're going to hit a constant speed and flat line from C on. If you wanted to draw it in the opposite direction, show it having a negative angular speed, that's okay. It would just look like that purple line there. For this problem, we have a merry-go-round shaped like a cylinder, and we're applying a force to the edge of it, causing it to rotate from rest to some speed. We also have a frictional torque that's going to obviously act opposite our pushing force in this case. So we first want to figure out how fast the merry-go-round is spinning after a period of time t. So let's start by drawing our free body diagram for all the forces acting on the merry-go-round. I'm going to say we have a pushing force here going in the counterclockwise direction. You could pick it to go either way, doesn't really matter. We're also going to have that frictional torque, which I will deal with in a second. Gravity is going to be going in. This is going to be the overhead view here. And we're going to have something supporting it from below, but we're not going to worry about those two. They're just going to cancel out. So let's think now about the torques we have created by these forces. So we clearly have a torque from this pushing force on the edge of our merry-go-round, and that's going to be going counterclockwise. And then we don't know exactly where this acts, but we do know that there's a frictional torque going the opposite way, about our pivot point in the center here. Now that we've identified our torques, let's go ahead and set up our sum of the torques equals I alpha. So we're going to have the torque from the push minus that frictional torque is equal to our moment of inertia times alpha. We can fill in a few things. So for the pushing torque, torque is RF sine theta. So I'm going to say R times the force of the push, which is just defined as F, times sine of 90, and that comes about because that pushing torque is tangent on the edge of the wheel, and that's going to form a 90-degree angle with our radius. So that's going to be a sine of 90 minus our frictional torque, which we're told is 1/4 the torque created by the push. So I'm just going to say this is 1/4 times RF sine of 90, and that's equal to our moment of inertia. For a cylinder, it's 1/2 mr squared times our angular acceleration. Our r's can cancel out here, and one of the r's from this term can cancel out. Sine of 90 is just 1, so that goes away as well. And so what we're left with is f minus 1/4 f, which is really 3/4 f, is equal to 1/2 mr alpha. And what we end up getting when we solve for alpha here is we get that our alpha is going to be equal to 3f over 2mr. Now that we have our angular acceleration, we can solve for how fast it's spinning. So we're starting from rest, accelerating at a rate of 3f over 2mr for a period of time t, and so we can solve for that final angular speed using one of our angular kinematic equations. So that final angular speed is just going to be that angular acceleration 3f over 2mr multiplied by our time, and so we get that our final angular speed is 3ft over 2mr. There we have part A for this one. We now want to know after time t the person stops pushing, how long does it take the merry-go-round to come to rest? Well, what we're going to have now is we're just going to have that frictional torque going the opposite direction, and so we can solve for our new angular acceleration. So that frictional torque was 1/4 RF sine of 90, and that's going to be equal to 1/2 mr squared, our moment of inertia, times alpha, and r cancels out once again. And what we end up getting this time is that our new angular acceleration is going to be 2f over 4mr, which is really just f over 2mr. We once again can set up angular kinematics. We know we're initially traveling at a speed of 3ft over 2mr. We're slowing down to a stop, and our angular acceleration is going to be negative f over 2mr. So we can set up angular kinematics once again and solve for our time. So we can say 0 equals 3ft over 2mr minus f over 2mr times t. We can move that one term over, and so we get 3ft over 2mr equals f over 2mr times t, and this is really t prime, the time we're solving for here. The f's cancel out, the m's, the r's, the 2's all go away, and what we're left with is just that t prime equals 3t, 3 times the time it took us to speed up. And that makes sense because if we look here, our acceleration while speeding up was simply 3 times our acceleration while slowing down, so it makes sense that it would take 3 times as long to slow back down to a stop. For the last part, we want to draw the motion graph showing the speeding up and slowing back down to a stop. So I'm going to label this first point as t, and then we have 1, 2, 3 additional t's for a total of 4t before we ultimately come to a stop. We were speeding up initially, so that's going to look something like that, and then we were slowing down to a stop, so that's going to look something like that graph. We could flip it over our x-axis, and then we would have speeding up away from the axis, and slowing back down, that would just be showing it with a velocity in the negative direction.